Hi, good afternoon again. So today we're talking about decentralized control, and as a little example we've got this little setup here. Here we've got a multivariable transfer function and we've got two possible controllers. The first one has got the controller as a diagonal matrix shown here, so we've got U1 is KP1 times error 1, U2 is KP2 times error 2, so that's one type of decentralized controller we could have. The second type of controller we could have was U1 is now a function of error 2 and U2 is a function of error 1. So the question is, which of these two controllers is most suitable? And that's what we're going to look at in the design of the decentralized controller. But just before we do that, I thought we'd just have a quick recap on multivariable poles and zeros as well. And we can remember one of the important equations is that the determinant of GS is given by ZS over PS. This gives us an expression now for a multivariable system to work out the zeros and the poles. And this is very vital in multivariable control. So we can have a go at applying that to this particular system here. So determinant of GS will be that times that minus that times that, because that's the GS there. So that's going to give us 1 over S plus 1 squared minus alpha over S plus 1, S plus 3. Now we can bring this under a common factor, which is going to be S plus 1 squared, S plus 3. And the top line will be S plus 3 minus alpha into S plus 1. So this gives an expression for the multivariable poles. So there's 1, 2, 3 poles, 2 at minus 1, 1 at minus 3. And this gives us an expression for the zeros. So we can take this expression now and rewrite it as S plus 3 minus alpha S minus alpha equals 0. There's our expression now for zeros. We can rearrange this as S into 1 minus alpha equals alpha minus 3 by taking that and that onto the other side. We can then take this underneath here, gives an expression that S is alpha minus 3 over 1 minus alpha. So now as we vary alpha, we can have different zero locations. So for instance, when alpha equals 2, then it'll be 2 minus 1, which will be, so ZS will be 2 minus 1, which will be minus 1, over 1 minus 2, which will be minus 1. So that's equal to 1. So when alpha equals 2, the 0 is at plus 1. So this is a non-minimum phasor because it's in the right half plane, so this is quite difficult to control. Let's say that we had alpha equal to 3. So in this case, the 0 will be 3 minus 3. So ZS will be 0 over 3 minus 1. It will be 2, which means the 0 is at the origin. Now if we've got a 0 at the origin, the control system is not possible to control, so we call it functionally uncontrollable. So if we end up with a multivariable system with a 0 at origin, we can't actually control it into the sense that we can make it carry out set point tracking. And that's always a constraint on any multivariable system. If we look at one more example, when alpha equals 4, then the 0 this time would be 4 minus 1, which would be 1, over 1 minus 4, which would be minus 3. So this time the 0 would be minus 0.333. So with a negative 0, this system now becomes relatively easy to control. Because the zeros quite dramatically affect the type of performance you might expect and the multivariable control system. So this is an important expression. GS is ZS over PS. Work out the determinant, get your expressions for your zeros and for your poles. Now in decentralized control, coming back to our example here, we want to figure out now which of these two controllers is suitable to use as a controller. Now sometimes both are suitable and sometimes only one. So in order to do this, we can compute something called the relative gain array, called the RGA. And to compute this, we work out G0, which is we get by putting S equal to 0 into this transfer function, and then we do a cross product with G0 to the minus 1 transposed. Now this type of multiplication is an element by element multiplication. What that means is if you've got a matrix, two matrices, and it's giving a third one, then you multiply that one by that one to give you that one. You multiply that one by that one to give you that one. You multiply that one by that one to give you that one. And you multiply that one by that one to give that one. So when we're working this thing out, we work out G0, then we work out G0 to minus 1, then we transpose it, and then we multiply them elements at a time. So that one times that one to give us that times that to give us that times that to give us that times that to give us that. Unfortunately, somebody's phoning me up, but I'll just ignore them. So we can apply this now to our system. So if we put S as 0 into here, we get the G0. So G0 comes out as, if S is 0, that becomes 1. If S is 0 here, becomes alpha over 3. If S is 0 here, it becomes 1. And if S is 0 here, it becomes 1. So now we have to work out the inverse of this matrix. And it will depend now on the value of alpha. So in this particular case, I'm going to choose alpha to be 2. So I'm going to consider the case alpha is 2, so that can become 2 in there. So the first thing to know is work out the inverse of this matrix. So swap these two around, change the signs on these, and divide by the determinant. So G0 to the minus 1 will be given by, I've got this over here, 3 minus 2 minus 3 and 3. So there's our G0, there's our G0 to minus 1. We then got to transpose this, so that means this row becomes that column, that row becomes that column. So that becomes 3 minus 2 minus 3, 3. That now is G0, this is G0 to minus 1, transposed. We now multiply them element at a time. So 1 times 3 is 3. 2/3 times minus 3 is minus 2. 1 times minus 2 is minus 2. And 1 times 3 is 3. So I've multiplied that one by that one to get that one. I've multiplied that one by that one to get that one. I've multiplied that one by that one to get that one. And I've multiplied that one by that one to get that one. Now, once you've got this matrix, this is called then the relative gain array. And looking at this matrix now, if you've done it correctly, each row and column adds up to 1. So this is clearly correct because it adds up to 1, each row and column. And to choose your decentralized controller, that's going to be this one, you have to choose positive numbers associated with this matrix. So the only positive numbers are that one and that one. So that implies that the only controller that will work is this one. So they've picked up the positive numbers, And so in this particular case, we could say that we've got an option between two controllers. This one would work, so that would be good. But this one definitely wouldn't work, so that would be bad. And this is how we can use the relative gain ray to determine which decentralized controller to use. In some cases, these numbers will add up to 1, but be both less than 1. So you could end up with a situation like 0.4, 0.6, 0.6, 0.4 in a different situation. So again, the numbers add up to 1, but in this particular case, you'd probably go for the bigger numbers rather than the smaller ones. So the bigger numbers would indicate, for this particular system, that this controller might be more efficient, but you could use this one as well. And the closer these numbers are to 1, the more probable it is that's the best controller. And that's the basic thinking behind the design of decentralized controllers.